Yeah, hi. So, good evening, everyone. We will start off the session in a minute or two. So, let me just share my screen. Yeah, yeah. So, let me just open my PPT PowerPoint. Yeah. So, good evening, everyone, and welcome to this session 8 on problem solving session for the course Advanced Power Electronics and Control. Um, So this will be the final problem solving session for the weeks of course, and tomorrow again we'll be having a problem solving session for the entire course, wherein we will be summarizing the entire course, and then we'll be seeing a lot of problems from different topics, so that of course you get to know more varieties in that, right, in problem solving session. So in today's session, we'll be covering the problems mostly on power quality and control of power electronics. So this is where the course actually ends as a graduate level course. So in this week, so far you would have seen or studied about power quality problems and use of filters for mitigating the power quality problems. So you have what are known as the shunt filters and the series filters, right? So among them itself, you have classifications which you might have gone through in your course. That is, you have the passive filters and then you have active filters. Correct? Right. So you did study about different topologies. So mainly you would have studied that they are the shunt filters or the passive filters are made up of passive elements, namely your L and C components, right? So that is you tune your values of L and C so that they resonate at a particular frequency, right? So the idea is that if they are resonating at a particular frequency, the as you know, harmonics consist of a lot of harmonics, right? You have first order, then the third, fifth, seventh, and so on. So what happens is that the frequency at which you are resonating that particular filter, right? So the frequency component of current that corresponds to that particular frequency gets shunted out or it gets filtered out. So that's the idea. So if it's a shunt filter, the idea is that the combination of L and C presents a very low impedance for that particular frequency of current, right? So that particular frequency of current gets shunted out. Okay. Or if it's a series filter, it would provide a huge impedance for that particular frequency. The idea is that you tune your L and C values. Basically, you do a kind of a resonance, right? So this is about your shunt filter, or this is about your passive filters. So as you can understand, passive filters suffer from a bit of disadvantages in the sense that, of course, when you design your values of L and C, you design it for a particular frequency, right? So, and when you put it the system, it is tuned at that frequency, no matter what. So you will not be able to dynamically change the value of the L and C so that you are able to filter out more frequency components, or you are able to vary the frequency, right? Right. So let's say you tuned it for fifth order and you find that even the seventh order is of significant amount, right? So you of course you understand that it cannot be varied dynamically. The other one is your active filters, right? So wherein you have devices or equipment such as StatCom, wherein you try to actively uh, do switching so that you are able to remove reactive power, or you are able to have a combination of L and C by doing active switching, right? So by doing that, you are actively you have an active control on what component you want to take out and for how much time you want to take out and stuff, right? So you studied about shunt and series filters, right? And you have the combinations of passive and active filters, correct, among them. Right. So that was one lecture, and later on you migrated towards what is known as state space modeling, right? So you went into a bit of linear control theory. So you of course studied that there is an overlap between linear control theory and electronics, wherein you apply principles of linear control theory for modeling of power converters. Okay. So the idea is that by doing state space modeling, what is known as state space modeling for effectively linear time invariant systems. So what you are doing is you are obtaining a linearized transfer function for the entire power electronic system, right? So you have L's and C's and diodes and switches, and you are somehow doing a combination of switching so that you are transferring power from your input side to the output side, right? So you may be doing a voltage step up or a step down, or AC to DC conversion, DC to AC conversion, or even in the case of DC to DC conversion, you may have isolated stages in them. Like people generally tend to do a DC to high frequency AC, and then you have an isolation over there, and then again high frequency AC to DC, right? So that's what you do in active front end converters or stuff, right? And of course, you have applications such as V by F control for induction machines, right? So wherein you try to vary the frequency itself. And apart from that, in the last week, you of course went through AC to AC converters, wherein you have regulators and of course you have matrix converters, cyclo converters, and stuff, right? So of course you understand that you have a lot of power conversion processes that are happening in all of these topologies. So the idea is that will I be able to model the system, right? So only if I can model the plant, right? So what do I mean by the plant? What I mean by the plant is actually the power electronic converter. If I am able to model the power electronic converter with mathematical equations, so if I can tell, okay, you have a black box over here, I give this input, so I get this output. How is the output expected to behave, right? So you may have changes in your input, you may have changes in your duty ratios or external perturbations and stuff. So if we can understand how the power electronic converter is going to behave for all of these perturbations or variations, so then it means that I have modeled my converter, right? So that is what we are trying to do with what is known as state space modeling. So what do? We assume that the power converter is basically a linear time invariant system. So you might have studied about LTI systems in your BTech courses or other courses corresponding to your control systems or signal courses, right? So what do I mean by a linear system, right? So if I might write it, right? So just give me a second. Let me just connect my charger over here. Okay. So coming back to what I was telling, so modeling is applicable for what? So modeling is applicable for LTI systems. So LTI means linear time invariant systems. Okay. So what do you mean by linear, right? So the idea is that if I have a system which follows the principle right? So, I mean, I call it a linear system. So, what do I mean by homogeneity, right? So, I guess you might be aware of these, but still, I feel it's important that we revise these things so that you understand how we make or how we approximate the power electronic converter into an LTA system so that you are able to do what is known as state space modeling, right? Okay. So, what you know is that in case of a linear system, you of course know that you have what is known as um, you have your superposition principle, and you know that you need to be it needs to satisfy the principle of homogeneity. So what do you mean by either of these? So that is, if I have a system wherein I let me take a different color over here, right? If I give x of t to a system, right? Then let's say I get an output y of t. Take the buck converter for example. You have, I mean, you of course feed V in voltage, and what you get? You get a V naught, right? So then the idea is that if I feed A into x of t, that is, if I just scale the voltage, right? If I do a linear scaling, then the output also needs to be scaled linearly. That's the idea, right? So if you feed A into x of t, you need to get A into y of t. Okay. So this is linearly scaled. So this is called linear scaling. This is one, right? And the other one is, of course, that, okay, so let's say you have x1 of t giving y1 of t, right? And let's say you apply another input x2 of t, and then you may get some y2 of t, right? The idea is that if you combine both of these, right? So if I just linearly add it, x1 plus x2, they should give, if I give feed an input equal to x1 plus x2, I should get an output y1 plus y2. Okay. So the idea is if these two conditions are satisfied, that is this over here and this over here, if these two are satisfied, only then I call a system as linear. Okay. So going back, so what do I mean by linear? If I can kind of combine both these terms that I have written over here, what I can conclude is something like this. Let's say I feed a into x1 of t plus b into x2 of t. This is my input. Then I must get a into y1 of t plus b into y2 of t. If this is satisfied, then I tell that the system is linear. Okay. And of course, you understand what is known as time invariant, right? That is, um, it should not be a direct function of time. Okay. So that's the idea over here. So you have linear time invariant systems. So with this approximation, we will go into a bit of state space modeling. Okay. So this is something that you will be doing in your master's level courses, maybe, wherein you will try to model a converter, and based on that, you will design what are known as controllers. Okay. So this is something that's very, very essential. State space modeling is something that's very, very essential if you want to design a controller for any converter, right? Okay. Um, so let me just go ahead over here. Okay, so I'll just take the example of a boost converter and try to model it, okay? So that you kind of understand what's the design procedure that we typically go through, okay? So then you will understand why I have called it linear control, okay? So there is a linear, I mean, there is a reason it's called linear control. Okay, so we'll just model it using simple KCL and KVL equations, right? We'll just model the converter and then you will understand. Okay, so of course, you guys know by now that this is your active switch. Let me call this S1, and this might be your diode D1, or it can even be a synchronous rectifier, so you might call it S2 as well. It's your convenience. Anyway, so the idea is that, so how does a converter behave? So any converter, to understand its working, what you do, you just split or you try to understand its working during the D interval when the switch is on and when the switch is off. So what do I mean by the D interval or the duty interval is when the switch is kind of on. Okay. So S1 is on and S2 is off. Right. So that's the idea. So what happens over here is, of course, this S1 is on, therefore this is a direct short over here, and there is no connection through D1. Okay, so of course it is simple to model. What you might expect is, of course, this inductor charging up during this interval, and this capacitor is going to supply your load. Correct. Okay, so that is why over here VL, if I define this is VL, okay, from this to this, and I define this as the inductor current, okay, and let me tell this is my capacitor current, okay, IC. So note the convention that I am following over here, right? So this is V naught. So Let me write it in a better fashion over here for you guys to understand. Okay, so you have, this is my convention over here, and let's say this is my conventional direction of capacitor current. Okay, so you have your VL and IC is something like this, right? So of course you can understand, right? And let's say this is my load V naught. Of course you can understand that VL is equal to V in or VI, right? And your IC is equal to minus V naught by R. This is your conventional direction of output current, I naught minus V naught by R. Simple enough, right? So this is during the D interval. And what happens during the other interval? Obviously, you understand that there is no connection through S1 because S1 is turned off, and because the inductor current needs to be continuous, this diode over here, right? The diode over here gets followed by us. Okay, so during this interval, what you can understand is your VL is going to be VI minus V naught, right? You just see the potentials over here. You have V naught over here and VI over here, right? So VL is going to be VI minus V naught, and what is your IC? IC is going to be IL minus V naught by R, right? So this is your IL. So IL minus I naught, right? Or IL minus V naught by R. So that's why I have called this as the D dash interval, right? So you have two distinct expressions for VL and IC. Okay, we typically call VL and IC as the state variables. Okay, why are they called the state variables? Based on the state of the device, whether the device is on or not, VL and IC are going to change, right? Right? VL and IC are going to change. So that's why it's called the state variables. Okay, right. So, so these are basic expressions which I guess you guys are already aware of, right? So what's happening during the D interval and D dash interval for a boost converter. Okay, fine. With this knowledge, let us just plot the waveforms for VL and IC. So you understand over here for both VL and IC, you have distinct positive areas and negative areas, right? So you have VL is equal to VI during the D interval, and during the 1 minus D interval, you have VL is equal to VI minus V naught. Similarly, IC is equal to minus I naught during the D interval, and IL minus V naught by R during the 1 minus D interval, right? This is simple enough, I guess, right? So you have your IL over here and V naught over here. Okay, fine. So this is so far so good for a boost converter, right? So after this, what do we do? So what have we done so far? We have just analyzed the converter and we have modeled it, right? So okay, so we had the converter equations right now. So now let's do what is called as an averaging. So you know that, okay, so VL and IC are actually changing their values over one switching cycle, right? And you of course know that when the converter is in steady state, you tell that this area over here, right, the positive area of VL is equal to the negative area. Similarly, the negative area of IC is equal to positive area. So only then you call that the converter is in steady state, correct? So when do we tell converter is in steady state? Right? Only when the positive area and the negative areas are same or they balance out. Okay. So if you take the average value, right? If you take the average value of VL over one switching cycle, it should be 0. Similarly, if you take the average value of IC over one switching cycle, it needs to be 0. Got it? Okay. Fine. Okay. So yeah, you of course know that these are the equations during the D interval and the D dash interval, right? So this is what we did just a few minutes back. Okay. So with this, what can we tell, right? So and this, of course, are the waveforms of your state variables. So yeah, this is what we have done over here. So what is your VL average? As I was telling, VL average needs to be 0, right? Only then you call that these converters in steady state. So if you tell that your VL average needs to be 0, that is your positive and negative areas are same, that means that if I kind of algebraically sum up this area, right? So if I sum up this area, what is this area? This area is going to be VL on, right? This is the on period into DTS, correct? And what is this area? This is going to be VL off into 1 minus DTS. This is going to be VL off into D dash TS, right? So if I sum up these two areas, I need to get a 0. Got it, right? Simple, because the areas are same. Okay, so if I sum up these two areas, I need to get 0. So that is why over here, D into Vi plus D dash into Vi minus V0. So VL on is your Vi and VL off is your Vi minus V0. You understood, right? Therefore, your VL is actually D into Vi plus D dash into Vi minus V0. Okay, so you just kind of expand these, you will get this expression Vi minus D dash V0 equal to L di by dt. Correct? Okay. And similarly, you do the same for IC, wherein your average value of IC over one switching period, this is also over one switching period, is 0. Okay. So what do you mean over here? That is your positive and negative areas are same. That is IC on into DTS plus IC off into 1 minus DTS is equal to 0. Right. So let me just make it simpler for you guys over here. That is you have IC into DTS plus IC on into DTS plus IC off into D dash TS, right, is equal to 0. That is this area and this areas kind of balance out or they cancel out. Correct? So the idea is that, so what is IC on? Or when during the D interval, IC is equal to minus V naught by R, and during the 1 minus D interval, it is IL minus V naught by R. Correct? So you do the same thing over here. D into, you find the area, right? So this area is, or this width is actually DTS, and this is actually D dash TS. Correct? So D into minus V naught by R plus D dash into IL minus V naught by R is equal to C dV dt. Okay. So we have substituted this over here, and mind you, during the steady state, what do we mean by steady state? That is LDI dt is 0, right? During over one switching interval, right? That is, there is no net gain of inductor flux, right? Or the capacitor charge. Okay, the capacitor charge neither increases nor decreases, right? Okay, so if you equate it to 0, you will get the converter expressions for during steady state, whatever you obtain during steady state. Okay, that is Vi will be equal to D dash times V naught, right? So taking this expression and equating it to 0, LDIDT is 0, right? Therefore you can write V naught is equal to Vi by D dash or Vi by 1 minus D, and this is your expression for a boost converter. Correct? So just we have just formed simple expressions. Okay. And one more thing. Okay, so this is a way of checking if you have done it correct. And one more thing is that, so what does it mean? In steady state, we tell, okay, the average value of VL over one switching cycle is 0. Average value of IC over one switching cycle is 0, right? Or in the expressions also, or in the waveforms as well, you can see that as I was mentioning, the negative area and the positive areas are same. So what do I mean when I tell that the negative area and the positive area is same? That is, the idea is that there is no net gain, right? There is no net gain in the capacitor charge or the capacitor current, or of course the capacitor charge. Okay, there is no net gain. Correct? Okay. So there is no net gain in the inductor voltage. That is, this is called as inductor flux balance. Okay, and it's called capacitor inductor flux balance and capacitor charge balance. Okay, it means that there is no net gain in the inductor flux, no net gain in the capacitor charge. Okay, that is the capacitor's voltage will not exceed. So VC is fixed. Similarly, IL is fixed. Okay, it's a capital IL which is fixed, and it's a capital VC which is fixed. Okay, so that is, so obviously understand, right? V is equal to L di dt. Correct. So if you tell that the net value of V is zero, then it means that the di dt is zero. Right? There is no net increase in inductor current or yeah. Okay. So we have done what is known as averaging. Okay. So now this is where we apply the concepts of basic control theory. Okay. So what do we do over here is a process called perturbation and linearization for an LTI system. So this is something we follow genetically for all LTI systems, and this is what we want to apply over here as well. Okay. Okay. So what do we do is basically you have these expressions which we just formed. You have your expression for let me erase this. You have your expression for the inductor voltage and the capacitor current, correct? So right. So now what do we do is a process called perturbation, right? So what do we do by so without going into perturbation, let's take your diode, right? Your diode characteristic is something like this, right? Right. So in order to find out, or in if we have to tell that this particular area is or this particular slope is linear, what do we do? This, let's say this is your operating point. What we do is within that very small area, we assume that the characteristic is linear, correct? We assume that over here the characteristic is linear. Okay, only then we will be able to write something like your R is equal to RD is equal to delta VF by delta IF of the diode or forward current of the diode. Okay, that is we linearize at a particular vicinity around the operating point. So if you tell that your operating point is capital D and your input voltage is VI, right, and your inductor current is IL, output or the capacitor voltage is V naught, what we mean really is in the vicinity of this duty. If I have a small variation in duty, D tilde or D hat, whatever you may call it, okay, if I have a small variation in duty or if I have a small variation in the input voltage, okay, this V tilde is it's like a delta D. Okay, it's a very small change. Okay, then how is my IL going to change or my V not going to change? I assume that for a small change in D tilde or small change in duty, my change in inductor current and output voltage are also going to be linear. Okay, or they are going to follow something like this, right? So D is equal to D plus D tilde. That is, capital D is the operating point, D is the DC, steady state operating point, steady state duty. Like this VI is the DC steady state input voltage and stuff. Okay. Then how is my inductor current going to behave and output voltage going to behave? Okay. So what I will do is in this expression over here, in these two expressions, I will replace all the state variables, right? All the input variables and the state variables with these. Okay, I will write IL as capital IL plus IL tilde. V naught as capital V naught plus V naught tilde. Okay, and the duty is a capital duty or DC steady state duty plus a small variation somewhere. Okay, right. So I will do the same over here. Right, I'll just apply in these expressions. Okay, I'll just erase these. Okay. So what happens if I kind of or if I kind of substitute all my equations with these tildes, right? So what happens is something like this. You can just substitute it. You can take this as an assignment and you can just solve this, right? So in this particular expression, okay, you just substitute. And similarly over here, you just substitute. So you will end up with dIL by dt and dV naught by dt. Okay. So you will be getting expressions in terms of tilde. So it gives you by how much my inductor current is going to change, by how much my V naught is going to change, and it will give a relationship between V naught tilde, Vi tilde, and D tilde. Okay, so if I have a variation of D tilde, how is it going to affect my inductor current? If I have a variation of D tilde, how is it going to affect the capacitor voltage? Right? So this is simple. You just need to substitute over here, and you will get these expressions. Okay. With these you can what you can do subsequently is you can apply Laplace transform. I'm not going into that, it would be more into control systems, but what you will end up is basically your converted expression, that is V naught by D. You will get an expression of V naught by D, that is, you of course understand that in any transfer function, right, this is your input and this is your output. Basically transfer function is input by output, right, in your Laplace domain. So this is your input and this is your output. So what you understand is you will get an expression of V naught by D, okay, where for a perturbation of D or D hat, how your V naught is also going to change, okay, and it's going to follow this particular relation, and this defines your plant. Okay, what's your plant? Your entire converter. So what you have effectively done is we have modeled our entire power electronic system or the boost converter over here, and we arrived at this particular transfer function. Okay, so now you can apply any particular aspect of your control systems concepts. You can try to understand what will be the rise time or all those. You can do time domain analysis, right? You can do stability analysis. You can do stability analysis, and you can do frequency domain analysis. Frequency domain. Okay, you can of course do frequency domain analysis, right? So you can study the stability of the converter, right? So for example, over here you see that you have a denominator of second order, right? So you have an square term, which means that um, if you have a square term in the denominator, sorry, right? If you have an square term in the denominator, you know that the typical expression is something like 1 plus S by Q omega naught plus A square by omega naught square. Correct? So this is a typical second order expression wherein Q is your quality factor and omega naught is your natural frequency or the resonance frequency of your converter. So you know what's the natural frequency of your converter, and you of course you understand that it's not only dependent on LC, it's also dependent on your duty. Correct? Or you may have studied in control systems as something like this: A square plus 2 epsilon omega ns plus omega n square. Correct? Of course, you can correlate with these, right? So where epsilon is your damping factor, you can obtain an expression between Q, your quality factor, and your damping factor. You can see how the system is damped, whether it's underdamped, overdamped. Of course, you understand that damping is dependent on your R. Correct? A lot of analysis can be done. You can study its stability. You can apply RH criterion, or you can see its Bode plot, right? Okay. So one thing that people typically do with this plant transfer function or the converter transfer function is, okay, so now that I have this converter transfer function, I know its resonant frequency and how it behaves. I essentially have its frequency response, right? With log f, I will have a magnitude A. So you will typically see that the converter transfer function looks something like this. Okay, this is your omega n. Okay, so what people typically do is they define or they design controllers and compensators for this plant. Okay, so let's say you want a crossover over here. They will design controllers so that your effective transfer function crosses over here itself. Okay, so you can do a lot of control systems concepts, so that's for a different course altogether. But anyway, you understand that modeling gives you a lot of advantages. So that's the reason we basically do state space modeling for any converter. It's not just that we design the converter and do switching. We want to run it in closed loop, right? So of course you understand that over here you can change the duty. If it's an open loop, you can just change the duty from 0.5 to 0.8 or whatever. But while it is running in an actual converter or in an actual system, you cannot go and manually change the duty every time, right? So based on the battery voltages, you want the duty to vary dynamically. You may have a battery at the input or the output, so the input battery may get discharged, so the input voltage itself may change, or your output side battery may be charging up continuously. So you want your duty to change so that you're able to maintain a particular value, right? So the idea is you have closed loop control systems for that purpose, wherein you try to control your inductor current and your output voltage, right? So for that, for designing closed loop converters, right, you need the plant transfer function. Only based on this, you design controllers. Okay. So you understand that for design of controllers, you need what is known as a feedback. Correct. So um, let me just get rid of some extra stuff over here. Okay, right. So this is how your closed loop controller typically looks like. Let's say you need a reference of 48 volt. Okay, right? You need a reference of 48 volt. Let's say initially you have only 40 volts at the output. Then what would happen is you have a 48 volt and a 40 volt. Okay, let's say the gain is 1 for this. Essentially, basically this voltage sensor. Okay, but let's say for now it is 1. Okay, let's say the gain of the voltage sensor is 1. So you have 40 volts coming over here, and you have a summer, okay, or a subtractor block over here. So what it would do, it would give you Vref minus Vs, right? In this case, 48 minus 40, which is 8 volt. It is then fed to a controller. Okay, so what it will do is it sees an error over here, right? The error is actually, basically error is Vref minus Vs, correct? So it would see an error over here and you have an 8 volt error, right? So it is then fed to the controller or the compensator. Okay, it's then fed to the controller or the compensator, and then it gives you some corrective action, which is then fed to the PWM, and based on that, the duty is very dynamically. Okay, so the duty varies so that the output reaches 48 volts from 40. So from 40, it may increase to 42 initially. Then the error again changes to 6 volt, right? Then the duty changes to D2 maybe. Then the voltage may increase to 46 and something like that. You understand, right? It's a closed loop feedback process. So as the voltage increases from 40 towards 48, the error will change, the controller's corrective action will change, the output will change, so that duty will change. Okay, if the duty changes, obviously your V naught changes, right? So that it reaches 48, and at 48, whatever is the operating point, it maintains over there. Okay, so that's the idea. You get it right. So yeah, so this is how your typically closed loop system operates. It's a very broad overview of how things operate, but nonetheless, this is just an idea. Okay, so you understand. So where did we start? We started off with basic converter modeling. We tried to understand how the converter behaves in the D interval and D dash interval, right? So we drew the equivalent circuit for that, and we just model the state variables VL and IC during the D period and D dash period. Okay, following which, what we did told was, okay, in steady state, what happens is your areas are same, right? Okay, you have what is known as flux balance and charge balance, right? So your LDIDT, net LDIDT is going to be 0. Okay, during average, or if you average it over one switching cycle, over one FS, okay, or one switching cycle. So VL is basically the area over here, right? So that is VI, or the average value of VL. So D times VI plus D dash into VI minus V naught. Okay, the area. That's equal to LDID. Okay, and similarly IC is CdVdt, right? Okay, so you got these, and then what we did was something called as a perturbation and linearization. Okay, so what we told was, okay, so if I have a steady state operating point D, I can tell that in its vicinity of D dash, I can linearize the converter. Then if I have a perturbation from D dash, what is my V naught? Okay, something like this. So similarly, we did for DVI, IL, and V naught, and we just replaced them in this average expressions over here, and then we had obtained what was di by dt and dv by dt, right? Okay, so I got di dt and dv dt, and from this we just told we could apply what's known as Laplace transform and end up with the converter transfer function, that's V naught by d. Okay, with this, if I can obtain V naught by d in Laplace domain, that is, you have S terms over here, right? We told that I can do time domain analysis, then stability analysis, and then frequency domain analysis. All of these three can be done. Specifically, we will focus on frequency domain. Okay, so we will focus on frequency domain, right? And then we saw a typical feedback system wherein if there is a difference in V naught compared to Vref, then you have an error voltage over here, right? Then the error is fed to the controller or GC of S. GC of S is the controller, right? It's fed to the controller, which gives appropriate input to the PWM pulses, and then an appropriate duty is generated. Okay, so based on the variation in duty, your V naught obviously varies, right? Once your V naught increases or decreases, based on that, again the error takes corrective action until steady state is reached. Okay, so in how much time steady state is reached, how much time the error is mitigated, all of that depends on what kind of controller you use. You can use fast responding controllers or slower controllers. It depends on a lot of stuff. Okay, but anyway, understand that you have a plant over here, that is GVD of S, we call it, because it's a transfer function between V naught and D, right? So you call it GVD. Okay, so you have the GVD over here, and for that you design GC. Okay, it's a separate design process is there, but of course that's for another course. But you understand why we need to do this steady state modeling, right? So it gives you a perspective of why you should do stuff. Okay, okay. So this was about some introduction to converter modeling, which I thought was essential. Okay, so let's go ahead with solving a few questions. So, okay. Okay, so at this point, please excuse me for just a second. I'll just have some water. Yeah. So okay, so we'll just go into a bit of problem solving. So we have a lot of theoretical questions over here. So we can see uh, both numericals as well as theoretical problems in this class. Okay. Okay. So the first question is, what is used for critical loads where temporary power failure can cause a great deal of inconvenience? Okay. So the options are SMPS, MPS, UPS, and RCCB. Okay. So you might know of all of this stuff. So SMPS is your switch mode power supply. Okay. And MPS is modular power supplies. UPS is your uninterrupted power supply, right? And RCCB is your residual current circuit breaker. Okay. So so you might understand, or you might guess the answer is UPS basically, correct? Because if you see the general architecture of basically SMPS or UPS, you know that in a switch mode power supply, you basically have an AC source or maybe DC sources, right? And the idea is presence of AC source is necessary. Then what you do is you kind of rectify it over here, and then you can have something like a flyback converter over here, and then feed, or you get V naught. Okay, this is your flyback converter, correct? Or over here you have the diode bridge rectifier DBR, right? And then you can have series regulators or low pass filters, right? So based on BJTs or stuff, right? Based on BJTs. Whereas in UPS, you have an AC to DC stage, correct? You have an AC to DC conversion, and after that, your idea is you store them in a battery, correct? You store the voltage in you obtain a voltage over here, and you stored the energy in a battery, right? So when your power cuts goes off, right? So when your AC goes off, the idea is this battery is able to supply your load, right? So then you have inverters, and then you can um, use your battery to supply your load, right? So the answer is obviously UPS, right? So when the power goes off, you can always use your battery, which is your backup, correct? And as long as your battery does not discharge completely, you can use UPS. You might have them in your homes or stuff. So the idea is answer is UPS. You of course have them in your homes, correct? So in HVDC transmission lines, both these stations operate as inverter, both these stations operate as converter. One acts as a converter and the other as an inverter, depends on the type of load. So in HVDC transmission line, so how does the system operate? Okay, so you understand that you have AC coming over here, typically let's say 50 hertz, correct? So it is then converted from AC to DC. Okay, so then you have the transmission line, and again you have DC to AC conversion. Okay, this can be AC of 50 hertz or 60 hertz as well. Okay, 60 or 50 hertz, again it can be 60 or 50 hertz. Irrespective of that, you understand that you have an AC to DC conversion block over here, and again you have a DC to AC conversion block. Okay, so this is the idea. Okay, so understand that one of these stations operate as a converter, and the other is an inverter. So this is your converter, right? And this is your inverter. Okay. Okay. So yeah, of course, this is a slide that enumerates the advantages and disadvantages of HVDC transmission. Okay, so for HVDC, you understand that it's more economical over long distances, right? And you can, of course, have asynchronous interconnections. What do I mean by asynchronous interconnections? That is, let's say I have a 50 hertz grid and you want to connect it to a 60 hertz grid. Okay, and it's of course economical over long distances, not for short distances. Of course, that is, you have something called as a break-even distance. Okay, so let's say this is the cost versus distance, correct? So as your distance increases, your cost is lesser. Okay, for or let me draw it the other way around. So this is your distance versus cost. So as distance increases, cost also increases in case of AC. Whereas for HVDC, you will see a curve something like this. Your cost is very high, and later on, if you see, the cost kind of drops down for higher distances. Okay, for HVDC. Okay, so you have what is called as a break-even distance. Beyond a particular distance, this becomes more economical. Okay, or you may have something like this as well, but this becomes more economical. Okay, so you people generally use it for higher distances or longer distances, and of course for asynchronous interconnections. Okay, so what are the disadvantages? And of course, you understand that you need to have two converters, right? That is, we saw earlier itself that you need an AC to DC conversion stage and DC to AC conversion stage. Mind you, both of these are for the rated power. Okay, and of course, the voltage level is going to be really high. Okay, so expensive converter systems, and you have a lot of converters, so the reliability goes down and stuff. Okay, but typically people use it for longer distances and asynchronous interconnections. Okay, so in this you can have multiple varieties, right? So you have what is known as a monopole system, wherein you have AC three-phase to DC conversion. Okay, and then you have the DC line over here, and then DC to AC conversion. Okay, with respect to a single ground. So you have just a plus DC with respect to ground. Whereas in a bipolar system, right? So you have a three-phase AC to DC conversion, but mind you, there is a midpoint ground. Okay, so you can have plus DC with respect to ground and the minus DC with respect to ground. Okay, so if you are transferring 100 kilovolt, over here it will be plus 100 kilovolt with respect to ground, and over here it will be minus 100 kilovolt with respect to ground. So a total of 200 kilovolts. It's your voltage level. Okay, so you have bipolar systems and unipolar systems depending on whether you use plus DC or plus DC 0 and minus DC. Okay, fine. For high power applications, dash are used as static switches, whereas for low power applications, dash are used. Transistors, SCRs, diodes, and stuff. Okay, so you may typically know that for high power applications, generally SCRs are used. Okay, and for low power applications, MOSFETs or thyristors or transistors are used. Okay, so SCRs or thyristors. Okay. Okay, so the idea is generally for low power applications, we go for higher switching frequencies. High switching frequencies, and this may operate at very low frequencies or even 50 hertz, the line frequency. Okay. Let me rewrite it over here. Okay. Okay. So yeah. So this is a graph that shows power as a variation of your frequency. Okay. So you understand that at for higher powers, right, in megawatt level or even hundreds of kilowatt, thyristors are typically used, and they generally switch at line frequency or even less. Okay, or generally switch at line frequency. Okay, so that's why you see that up to 100K, this is in log, right? It's in logarithmic scale. So up to maybe 100 frequency or 100 hertz, thyristors or ACRs are used. Okay, whereas MOSFETs, on the other hand, they are used for high frequency, or very high frequency and low power. Okay. So mainly in power electronics, we deal with IGBTs, thyristors, and MOSFETs. You understand that IGBTs can be used for motor drive applications, so maybe in the mid-frequency range, right? So a few hundreds of hertz to maybe a few hundreds of kilohertz, not more than that. Maybe 10 or 20 kilohertz, not more than that. IGBTs. Okay, MOSFETs can be used up to maybe megahertz level or even more than that, right? You have gallium nitride HEMTs which are used in the megahertz level. Okay, but thyristors, ACRs cannot switch at very high frequencies, so they are generally used for DC, AC to DC converters or rectifiers. Okay. So thyristors and ACRs are used for high power and low switching frequency applications, and transistors are used for low power and high switching frequency applications. Okay. Fine. So the idea is, or the answer is, for high power applications, ACRs are used, and for low power applications, transistors are used. Okay, or MOSFETs are used. Okay, right. So over here we have a numerical problem, right? So determine the loss of this number circuit if C is equal to 0.545 microfarad and supply is 221 volt at 10 kilohertz frequency. Okay. So from the given problem itself, you can understand that the energy dissipated in the capacitor is going to be half CV square, right? So what is the power? Power is basically dE by dt, or the energy multiplied by the frequency, right? So the power is going to be half CV square into Fs. So you know what is C, you know what is V, and you can find out what is uh, the power, right? So that's going to be half into 0.545 micro into V square is 221 square into 10K. Okay. So we will typically get around maybe 133 watt. The answer is this. If you let me just calculate over here. One find 0.545 into 121 into 121 into 10K. Yeah, so you will be getting 133.09 watt. Okay, so or 133 watts. So this is typical snubber circuit, RC snubber, that's actually shown over here. You have the switch over here, right? It can be a MOSFET. Okay, and across that you have your R and C, okay, which is your snubber. So it controls the dV by dt across the switch. So the snubber, why do people generally use snubber? they basically slow down the device, right? So you have an extra C in parallel, right? So the C effective is going to now be CDS plus some capacitance which is in parallel, correct? So you have a larger capacitance. Therefore, your RC time constant increases. Okay, so your DVDT is slowed down. Okay, so basically people don't prefer very high DVDTs due to a lot of EMC issues or EMI issues. Therefore, numbers are involved or employed. So yeah, so this is the way to calculate it. So you can calculate your power, which is a multiplication of energy times your frequency. Okay, and then your energy is half CV square, and you just substitute the values, you end up with the power. Okay, fine. So let's move on to the next question. Two 6-pulse converters used for bipolar HVDC transmission system are rated at 1000 megawatt plus or minus 200 kilovolt. Okay, what is the DC transmission voltage? Okay, so is it 200 kilovolt, 400 kilovolt, 500 kilovolt, or 100 kilovolt? Okay. Okay, so given it's a bipolar system, right? So what did we say in bipolar system? It means they want to tell that the DC voltage is basically 200 kilovolt. That is, you have a plus DC and a minus DC of 200 kilovolt. Okay, and you have the ground over here. So what is the total voltage? It's going to be 200 minus of minus 200, right? So the total is going to be 400 kilovolt. So the answer is this. Got it, right? So you have a plus DC of 200 and a minus DC of minus 200. So the total is going to be 400 kilovolt. Okay. So you have the HE three phase over here, right? And you have you basically convert AC to DC, and then you convert DC to AC. That's your HVDC system. In the middle, you have the DC line, and in a bipolar system, you have the midpoint ground over here. Okay, so the total voltage is going to be plus DC minus of minus DC. That is 2 into DC. Okay, that is 2 into 200 kilovolt, which is your 400 kilovolt. Okay. Yeah, positive DC line potential with respect to ground is 200 kV, and similarly for negative DC line potential with respect to ground is going to be minus 200 kV. Therefore, the total potential difference is going to be 400 kVs. Okay, fine. Okay, so the next question is the converter circuit which employs turn on and turn off when the voltage or current through the device is zero at the instant of switching is dash. A conventional converter, multi-level converter, matrix converter, or a resonant converter. Okay, so read the question properly. Which employs turn on and turn off when the voltage or current through the device is zero. Okay, it means that the switching losses zero. Okay, that is, it will turn on at ZVS or ZVS. It's called zero voltage switching, and it will turn off at ZCS, zero current switching. Okay, so the idea is that, so if I have to go into a bit of converter basics, okay, or switching basics, what happens is, so let's say we are talking turn on, correct? So let's say we are talking about turn on. You understand that your voltage is going to fall, and approximately you can also tell let's say I turned on the device over here. The current will start increasing from this point, right? So I understand that there is an overlap. Okay, there is an overlap of V and there is an overlap of current. And this voltage may be really high, maybe let's say a 400 volt, and let's say the current is 30 ampere. So there is a huge power loss, right? 400 into 30 amperes for a very short period of time. It may be in the order of a few nanoseconds, but nonetheless, this loss is quite high. Okay. So what's the energy over here? You understand that the energy is going to be 1 by 6 times, because voltage is falling and current is rising. So 1 by 6 times V into I into this T on, if I may call it. Okay, so what's the power switching loss? Is going to be E into F. So you understand that every time the device turns on, this loss is going to happen. Correct? Every time the device turns on, this loss is going to occur. And every time the device turns off, this loss is going to occur. So these are known as turn on losses. And you analogously, and by a similar analogy, you can also tell that there is going to be something called as a turn off loss for the converter. Okay. Okay. So this is your hard switching. So this is what is called as a hard switching. So what do they mean in the question when they tell that the converter is turning on or turning off at zero current or zero voltage? Is that so during this period, you understand that my loss is going to be something like this. That is going to be a huge loss, correct? So this is my power. There is going to be a huge loss. Okay. You consider the case, let's say if your voltage falls to zero, and let's say my current starts rising from this point after my voltage has fallen to zero. Okay. So then there is no overlap, right? So no overlap between V and I. Okay, there is no overlap between V and I. So that is my current is starting to rise after my voltage has fallen to zero. Okay, after voltage falls to zero, my current is starting to rise, right? So it means that there is no overlap between V and I. Okay, there is no overlap between V and I. So in that case, there will be no switching loss. Switching loss is going to be zero during this period. Okay, so during this period, my switching losses are going to be zero. Okay, fine. So my switching loss are going to be zero. And similarly, for during turn off, you will see that um, first the current will fall, only after that the voltage is going to rise. Okay, so you have your ZVS over here, that is zero voltage switching or zero voltage turn on. That is the device starts conducting current after the voltage has reached zero. That's why it is called zero voltage switching. Okay, so that's why this is called as zero voltage switching. Okay. Okay, fine. um Fine. So what kind of converter gives this? So there is a class of converters known as resonant converters. Okay. So they have resonant LC networks, which are tuned to a particular frequency. Okay. In this case, the tank network or the LC network is actually tuned to the switching frequency. Let me on my turn on my laser pointer. The tank network is basically tuned to the switching frequency. Okay. So the idea is that by tuning it, I'm not going into the operation. The idea is that it can give you zero current switching or zero voltage switching. Okay. So using resonant converters, you can of course achieve the objective of zero voltage turn on or zero current turn on. Basically, you are making the switching losses zero. Okay. Okay. Um. So the reverse recovery time, we will move on to the next question. The reverse recovery time of a diode is TRR is 3 microsecond. Okay. And the rate of fall of the diode current DI/dt is 30 amperes per microsecond. Determine the stored charge. Okay. So yeah. So you can just by inspection you can tell that your total charge is going to be current into T, right? Correct. So because I is equal to Q by T. Okay. So they have given you di by dt. So di by dt is given and the t is also given. Correct. So dimensionally you need to do something like this. But let us go into a bit of understanding reverse recovery. From that, once you understand reverse recovery, it's a cakewalk to get the answer. Okay. So the reverse recovery time is given and the di dt is given. Okay, so you understand that what happens in reverse recovery is basically this, right? So when you turn off the diode, the forward current falls. Okay, let's say this was a forward current. It falls to zero, and after that it goes to a negative, correct? It goes to a negative peak, which is called IRR, and then it comes back to zero. So the total area over here, right? The area over here gives your stored charge, right? This gives a stored charge or QRR. They are asking what is QRR basically in this question. What is QRR? So in this graph, if you are able to find out the area, okay, if you are able to find out the area, you will be able to get what is QRR. Okay, if you are able to find out the area, you will be able to get what is QRR. Okay, so it's just area of a rectangle triangle. You understand that it's basically going to be half into base into height, right? So half into IRR into the time TRR. Okay, so that's what we have done over here. So what is IRR? IRR is basically again di by dt into TA, right? Over here. So IRR is equal to slope into time. Correct? Slow. So di by dt is also given, which is 30 ampere per microsecond, and the time is also given, right? TRR is almost 3 microsecond. Over here, you see that TA is much greater than TB, right? And therefore, TA is almost equal to TRR. Though TA plus TB is equal to TRR, we tell that TB is very small. Okay, so TA is almost equal to TRR. Therefore, IRR is 30 into 3, which is 90 amperes. So this is your peak. Okay, slope into time, right? So this is your peak. Once you have this, so half into IRR into TRR, right? So half into 90 into 3. Okay, so it should give you 45 into 3, which is 135 microcoulomb. Got it, right? So just it's the area of this graph, and if you know what's reverse recovery, you will be able to get this. Okay, fine. Yeah, so the answer is 135. Okay, the answer is 135 microcoulombs. Okay, so the DIDT is given and TRR is also given. So you just found out the QRR by just determining this area. Okay, and this area happened to be half into IRR into TRR. Okay, this is your QRR. Okay. Yeah. So we'll move on to the next question. So track is used in dash chopper, speed control of induction motor, speed control of universal motor, and none of the above. So you just try to understand what is track. So track, as you might know from your basic devices knowledge, is basically an anti-parallel connection of two SCRs. Correct? Correct. So this is your track. So this is your track. Okay. And you of course know that your SCR is actually a voltage bidirectional current unidirectional device, right? That is, the characteristic is something like this: voltage bidirectional and current unidirectional. Okay, so if you put two in anti-parallel, what's going to happen is you are going to get bidirectional current capability as well. So of course you understand that triac is a four quadrant device, right? So triac is a four quadrant device. Okay, so triac is a four quadrant device. So with this knowledge, yeah, of course I was telling triac is a four quadrant device and it can be used for alternating current. Okay, so you have control turn on and control turn off bidirectional current flow as well, right? Right. So you have control turn on as well as control turn off. Yeah. So typically it is used in universal motor control applications. Okay, and of course you understand that for universal motor you require bidirectional current capability as well as voltage blocking capability, and triac fits the bill. Therefore, um, triac is used in the speed control of universal motor. Okay, fine. Yeah. So just give me a moment here. I'll just have some water. Yeah, so we can just continue from where we left off. Correct. So look at the next question. Which of the following indirect matrix converters allows only by a unidirectional power flow? So we understand that in the converter topology, which has a diode in it, right? So because diode is a unidirectional current flow device, it's obviously going to allow only unidirectional current flow. So you just need to know the topologies of each of these, right? So yeah. So you have your sparse matrix converter over here, and of course you have IGBTs, right? So and of course in these you can see that you can get bidirectional current flow, right? Because you have on the bottom side, if you just have a look, so you have diodes in both directions, correct? So if this device is going to be on, yeah. So if your this device is going to be on, the current will go like this, and if not, the antiparallel diode is going to conduct, right? So it can give bidirectional current flow. Then you go to the very sparse matrix converter, and again you would see a battery of diodes, right? So when this device is on, of course the current will flow from A to this diode through the device, this diode, and through this. And for the reverse conduction, it can of course flow through the antiparallel diode, correct? But you look at the ultra sparse matrix converter, you see that it can allow current flow only in one direction, correct? It doesn't have any active switch over here. Okay. Therefore, the answer for this question is, of course, ultra sparse matrix converter. Okay. Okay. So the transfer function approach is applicable to what? Only linear time invariant systems, linear time invariant as well as time varying systems, linear as well as nonlinear systems, all systems. So of course we saw it earlier that it is applicable only for linear time invariant systems. So what do you mean by that? Linear systems, it should satisfy the principles of superposition, right, and homogeneity. Okay. So yeah, you can understand that the transfer function approach is applicable only to linear time invariant systems. Okay, fine. For an SCR, conduction angle is 120 degrees when average on-state current is 20 amperes. When the conduction angle is halved the earlier value. Okay, so if you tell that the conduction angle is now only 60 degrees, the on-state average current will be what? So you of course know that more the conduction time, right? More the conduction time, the average current actually decreases, right? More the conduction angle, the average current decreases, right? Because um, over here, you of course know that your beta is actually proportional to 1 by or inversely proportional to your on-state current. Therefore, therefore, what you might expect is at 60 degrees, the on-state current gets multiplied by 2. Okay. Therefore, it's going to be 40 amperes. Okay. Fine. So the ratio VRMS by VDC is known as what? Form factor, ripple factor, utilization factor, none of the mentioned. So this is a basic definition that you might have learned in rectifiers. That was the very first module that was taught in this course. VRMS by VDC is of course known as the form factor. Okay, form factor equal to VRMS by VDC. Okay. So SMPS are based on dash principle, phase control, integral control, chopper or MOSFET. So we did study in one of the previous modules that all SMPS are based on the chopper principle. That is, you have step down choppers, step up choppers, right? So you have basically the DC-DC converters, right? So all the SMPS are based on the chopper principle. That is, you kind of get a chopped voltage at the switching node, correct? So let's say you have a V in over here, which is a continuous wave. So you have a switch arrangement. which ensures that at this point you get something like this. Correct? So this is kind of a chop wave. Okay, this is the principle of any chopper or any SMPS. Okay, it's based on a chopper principle. Correct? Okay. So usually dash batteries are used in UPS systems. Nickel cadmium, lithium ion. Okay, I'm sorry, this is actually the lithium ion battery. So nickel cadmium, lithium ion battery, lead acid battery are all of the mentioned. Okay. So actually in UPS systems, mostly if you see commercial UPS systems, you will see that most of them use lead acid batteries. Although nickel cadmium batteries basically give better performance. Better performance, but they are way costly. Okay, 3 to 4 times costlier than lead acid. Okay, 3 to 4 times costlier than lead acid. Okay, therefore nickel cadmium is not preferred. Generally, lead acid batteries are used in UPS systems. Okay, because mainly of its cost, we don't prefer nickel cadmium. Okay, so choose the correct statement. MOSFET suffers from secondary breakdown problems. MOSFET has lower switching losses as compared to other devices. MOSFET has high value of on-state resistance as compared to other devices, are all of the above mentioned. Okay, so generally, MOSFET doesn't suffer from secondary breakdown problem. Okay, MOSFET has lower switching losses is one, and MOSFET has higher on-state resistance. Okay, so the answer is it has lower switching losses. That is why you are able to go at a higher switching frequency. Okay, so the answer is MOSFET has lower switching losses. That's why we already saw in one of the previous slides that MOSFET is typically used for MOSFET is typically used for very high frequency. MOSFET is typically used for very high frequency applications. Why? Because it has low switching losses. Therefore, you can increase the switching frequency. You know that as you increase switching frequency, your value of L and C are going to be lesser. Correct? Therefore, you can design very compact and power dense converters while ensuring that the system is also efficient. Okay, very small converters. So that's why MOSFETs are used for high switching frequency applications. Okay. Okay. Right. So MOSFET has low switching losses compared to other devices. That's why you are able to use for high switching frequency applications. And this brings us to the last question of the session for today. The voltage blocking capability of the IGBT is determined by dash injection layer, body layer, metal used for the contacts, or the drift layer. So typically the voltage blocking capability is determined by the drift layer, right? So irrespective of IGBT, any power device, right? For any power device, you know that even for a diode, for example, typically you have the P and the N regions, right? For a power, so this is for a simple diode or a signal level diode. However, for a power diode, you will see something like this: P plus, N minus, and N plus, a lightly doped region in the middle, and this is actually called as the drift layer. Okay, so this is called as a drift layer. So the width of the drift region is proportional to the voltage blocking capability. Okay, width of the drift region is proportional to the voltage blocking capability. More the width of the drift region, better will be the voltage blocking capability. Got it right? So the width of the drift region defines the voltage blocking capability of your device. Okay, fine. So, however, you may tell that, okay, so since the width of the drift region defines the voltage blocking capability, I will use 1200 volts rated or 1700 volt rated devices for all applications. However, it comes with a drawback. So as the width of the drift region increases, the resistance or the forward voltage of, however you may call it, that is also going to increase. Okay, so the losses are going to increase. Okay, it always comes at a cost. So you just cannot use very high voltage rated devices for all applications. Okay, you just need to choose the values judiciously. So the idea is that the voltage blocking capability is determined by the drift region. So this was more of a theoretical session. We just saw a few problems relating to that. Okay. Um, so this kind of brings us to the end of the say a problem solving session for today, and of course for this entire course. So tomorrow we will be having a summarization session for the entire course, wherein we will try to summarize, right? So wherein we will try to summarize all the problems that we have seen so far. Okay, from different modules, right? We will try to summarize all the problems we have seen so far from different modules, and we will see different kind of problems, okay, from each module. Okay, so that should give you an idea of how you might expect problems in your paper. So yeah, we will see quite a few problems tomorrow. Okay, so if you have any doubts, you can of course write to us. So thank you everyone for attending today's session. Hope today's session was useful for you guys, and yeah, see you tomorrow. Good night everyone. So I will just stop my camera and stop my mic. I mean, stop my sharing as well. Okay, so I will stop my mic and then I will stop recording. Yeah, so yeah, take care and good night, everyone. Okay.